Yes, sir. Now tell me. The third now, here VR is parallel to the current, means they both are in phase with each other. Now, who is in capacitor? Who is current is leading or lagging in capacitor? Leading by 90 degrees, right? So current is leading the voltage by 90 degrees. So can I write in the other words? VC is voltage in the capacitor is pi by 2 behind the current. Can I write like the same thing in the other way? Voltage in capacitor is 90 degrees behind current. Can I write like that? Here current is leading, no? Current is leading the voltage. Here current is lagging the voltage. So pi by 2. Can I write like that, Abid? Pi by 2 ahead of current. Can I write like this? Yes or no?
Yes.
Yes, sir.
See, here I wrote resistor voltage across resistor is parallel to current as per the phasor diagram. After that, here VC is pi by, that means voltage across capacitor. Here what happens? Current is ahead of voltage, or current is ahead of voltage. Is that clear now? Here means current is leading the voltage by 90 degrees. So the same sentence is written in the other way. Here current is lagging the voltage. So the same sentence is written in the other way. अच्छा अच्छा जाओ मार लगेगा now so take the screenshot of this, take a picture of this.
So I wrote it down.
Yeah, sometimes now going ahead. Okay, so this is about the, now I will draw the phasor diagram for this. Okay, I'm going to draw the phasor diagram for this. Now when I'm drawing the phasor diagram here, the phasor diagram is in this way. So all the three terms will come at the same time. Now this is the voltage with respect to current I am drawing now. This is VR, voltage across the resistor. Now what is happening? See here, VC is the voltage across the capacitor and VL is the voltage across the inductor. Okay, they are 90 degrees. See here, current is lagging in inductor and current is leading in capacitor, with capacitor. Current is leading the capacitor, current is lagging the inductor. Okay, inductive voltage by how many degrees? 90 degrees. And current is in series with the, like in phase with the voltage across the resistor. So this angle is known as omega t plus phi. Okay. Now what happens? Now this arrow is bigger than this arrow. Voltage of the capacitor across the capacitor is voltage is more than the voltage across the inductor. So you have to use the vector diagram. When you are using vector diagram, when we add it, what happens? This minus this, because it is in the opposite direction, we will get this vector. This vector is what? VC plus VL. Okay, VC plus, when we add both of them, it will become VC plus VL. And what will happen now? So this will be the current. I is the current. Okay, I is the current. Or we can also write, this is the VR. We are comparing voltages now. Now this is the resultant voltage. Okay, this is the resultant voltage, that is V. So is that clear? So I got this voltage and this voltage. Okay, I got these two voltages. See, when I add this voltage to this voltage, I am left with this voltage. Is that clear? That is VC plus V. Now what will happen? The resultant of these two voltages. Okay, the resultant of these two voltages. You have to complete the parallelogram. See here. You can complete the parallelogram. When you complete the parallelogram, this is the resultant voltage, is it not? So V is the resultant voltage. Is that clear now? Use the parallelogram law of vector addition. Now the angle between both of them is again here 90 degrees. Then this is what VC plus VM. This is VR. Okay, and this is omega t. Okay, this is omega t, and this is phi. This is phi, and this is VRM. Is it clear now? Is that clear, sir?
Yes, sir.
Okay, so this is known as VC minus VM. This value, this is VR. Okay, this value is known as VCM minus VLN. This is what VM. VM. Okay, then that is omega t. Phi is that. Is that clear, all of you?
Yes, sir.
Okay. Now I'm going to write that. Okay. I'm going to draw the diagram. One second. Did you understand this one?
Yes, sir.
Now what happened here? VRM is equal to IRM. Okay, VRM is equal to IR. VCM is equal to IM into XC. See here, V is equal to IR, but across the capacitor we don't have R. We have only reactance. That is said to be what? Capacitive reactance. And we have VLM. VLM is equal to what? IM into XL. Okay, IM into XL. So the voltage here is what? V is equal to what? V is equal to VL plus VC plus VR. Okay, the total voltage of the EMF, the voltage given by the EMF is equal to voltage across resistor, inductor, and capacitor. Okay, they are in the same line. VC and VL, they are in the same line, but they are in the opposite direction. Okay, so that is a magnitude. What is the magnitude now? VCM minus VLM. That is the magnitude. Okay, this is the magnitude. Okay, now and VR and VC plus VM are the sides of right angle triangle. Here VR and VC plus VM is so they are the sides of the right angle triangle. We'll apply Pythagoras theorem to this one. Okay, we'll apply now Pythagoras theorem. Is that clear now? See here, like what
Yes,
happens
sir.
now? So it can be like this, a triangle. See here, look at this, it will become a right angle triangle. This is VC plus VM, this is VRM. So we can draw this the resultant force. That is a what is that? Hypotenuse. Yeah, hypotenuse. So hypotenuse square is equal to what? Hypotenuse square is equal to opposite side square plus adjacent side square. VM plus VM minus VLM, VCM minus VLM whole square. So please don't get confused. This is something new. Okay, you are doing for the first time. It appears to be something new. It's not difficult, but it is very easy. Okay, see here, we have written all the voltages, then we added the voltages, and this is what is the magnitude. Okay, because the final one is the magnitude. That's the reason we wrote here. So this side is equal to what? This side, this is square. This square is equal to hypotenuse square is equal to opposite side square plus adjacent side square. We wrote it here. Now we will substitute that. What is V? Vm is equal to what? Vm square is equal to Im into R. Okay, Im into R whole square plus Im into XC, Im into XC minus Im into XL whole square. Okay, so what is V? V is equal to I into XC, VLM is equal to I into XL whole square. Okay, square that you are using the Pythagoras theorem. कबीर बंद करो अब बोले ना हाँ Pm square is equal to what? Im square into R square plus XC minus XL whole square. Okay, XC minus XL whole square. So what will happen now? Im is equal to what? Vm divided by under root of R square plus XC minus XL whole square. Is that clear? RC minus R square plus XC minus XL whole square. So we are writing here Im is equal to what? Im is equal to Vm by Z. Okay. What is Z? Z is the combined reactance. That is known as impedance. So sleeping. This is like this. That is Z is said to be what? That is said to be impedance. Okay, Z is said to be impedance. We don't have combined reactance. Okay, the resistance of the resistor and reactance of the capacitor, reactance of the inductor, all together, it is known as Z. That is said to be the impedance. Okay, so Z is equal to what? Z is equal to, we have the value over there. Okay, I is a phasor is parallel to VR. Now, what we are writing, the combined thing is like a right angled triangle. Okay, this is a right angled triangle, and this is phi, this is R, this is Z, and this is VC minus XC minus XL. This is known as XC minus XL. Is that clear? XC minus XL. Now, what will happen? You take tan phi. Tan phi is equal to what? Tan phi. Phi is the angle. So tan phi is equal to opposite side by adjacent side. Opposite side by adjacent side. Adjacent side is R. So this is the formula. So instead of writing that, we are writing here Vxm minus Vc minus Vcm minus Vlm divided by R. That is VR. This is the formula to calculate the angle. Is that clear now? Yeah. Okay. अच्छा, okay, बाद में. Now, so here we have. So this is about one. This is about the angle. Okay, this is the Z is said to be impedance. How do we define impedance? Once again, see here once again. DC is the voltage across the capacitor. VR is the voltage across the resistor. VL is the voltage across inductor. Voltage across resistor is in line with the current. Means there is no phase angle. They are in phase with each other. Now I am writing here if you take the resultant, see these two are in opposite direction. The length of this is more than this one. So we are using the vectors addition, vector addition. When we are using a vector addition, we got this one. Now using parallelogram law of vector addition, you draw one line here parallel to it, draw one line parallel to it. This is the diagonal. The diagonal is B. So Vrm is equal to IR, Vcm is equal to Imxc, Vlm is equal to Imxl. Now V is equal to VL plus VC plus VR. So Vcm minus Vlm. So this square is equal to this square plus this square. You have to add it. Now substitute the values and take common. So you are left with that one. So the formula is what? Im is equal to V by R. Okay, V by the resistance. That the whole thing is known as impedance. In simple words, what is impedance? Impedance is the resistance with the frequency component. Resistance, instead of writing resistance, we are writing impedance. Impedance is known as resistance with frequency component. Whenever we connect a components in AC, an alternating current or in the oscillator, across the oscillator, then we say it is impedance. Instead of writing resistor, we say impedance. So see, same thing. Suppose I drink milk at home. The same thing when I drink at restaurant, they say milkshake something. The name is changed. Is it not? The name of that is changed. Suppose I drink cold water at home. They say, do you want like a drink over there at one restaurant? They say soft drink or hot drink. The term is changed. The same way, same thing here. When it is connected to AC, then we say impedance. Okay, tan phi is the angle. Tan phi is equal to VCM minus VLM divided by VRM. That is the formula for that. Is that clear, all of you?
Yes, sir.
Clear, man. Okay, so the last thing before ending this topic, the first one. The next one is analytical solution. That I will do it tomorrow. Okay, so here let me finish up that one. So here, when I draw that, here I come to know that if XC is less than greater than XL, means inductive capacitance is greater than capacitive reactance is greater than inductive reactance, then phi is positive. The value of phi is positive, and then what happens? I leads voltage. Okay, and the circuit is said to be capacitive circuit. The circuit is said to be capacitive circuit. Similarly, if what happens if XC is less than XL, then what is that? Phi is what? the phi is negative and V leads current. Okay, and that is said to be inductive. That is said to be inductive. Is that clear now? So now what is the circuit now here? See, look at this one. This is the voltage. Okay, this is the final voltage.
Yes.
Final voltage. See, this is the final voltage, and this is the current. The current is how much? At an angle here. So the angle between both of them is phi, and this is omega t. This is omega t. Is it clear? What happens if they are equal? If it is equal, then it is a resonance. That I'll explain tomorrow. Okay, in the analytical solution. If XC is greater than XC, if the capacitive reactance
Okay,
is
sir.
greater than inductive reactance, then it is a capacitive circuit. If capacitive reactance is less than inductive reactance, then that is actually inductive circuit. Is that clear? So that completes the first solution. That is a phasor solution. The next solution is analytical solution that I will do it tomorrow with the resonance concept. Okay. So, and then we will discuss about the sharpness of the resonance and all. Okay. So that completes your topic. And we will be left only with, some definition, power factor, what less current and all. That is a small part, small topic. After that, we can start transformers, and after transformers, we can go with the generator, AC generator also. Clear? Just go through
Okay,
this.
sir.
If you have any doubts, you can ask me tomorrow. Is that clear? Abid, is that clear? Are you clear with the topic?
Yes, sir.
Okay.
Okay.
Okay. Thank you so much. We'll meet tomorrow.
Okay, sir.